A message in a bottle. This week on Planetary Radio. I'm Sarah Al-Ahmed of the Planetary Society, with more of the human adventure across our solar system and beyond. NASA's Europa Clipper mission is almost ready for its historic trip to the Jovian system. This week, my colleague Merc Boyan, a visual storyteller at the Planetary Society, takes you into the clean room at NASA's Jet Propulsion Laboratory to speak with the team members about the spacecraft. Then Bob Pappalardo, the project scientist for Europa Clipper, visits our headquarters in Pasadena, California, to share the story of the mission's vault plate, humanity's next collection of messages to another world. Our chief scientist, Bruce Betts, joins me in the end for What's Up and a discussion of our favorite messages from Earth. If you love Planetary Radio and want to stay informed about the latest space discoveries, make sure you hit that subscribe button on your favorite podcasting platform. By subscribing, you'll never miss an episode filled with new and awe-inspiring ways to know the cosmos and our place within it. You might notice that I'm a little croaky today, but don't worry. That's just because I spent the last day at the U.S. Congress speaking with representatives about space exploration. I might have used my voice up a little, but I tell you, that was an adventure, and I'm going to share that with everyone on a future show. But in the meantime, we'll talk about Europa Clipper. Think about what life needs to thrive here on Earth. A spark of energy, a splash of liquid water, and the chemical building blocks to form complex organic molecules. Now imagine a world not too far from us where all of these ingredients might exist. Jupiter's icy moon, Europa. Encased in a thick shell of ice, beneath which lies a deep, dark ocean, Europa presents a compelling case for life's potential beyond Earth. It's possible that Europa contains up to twice as much water as all of Earth's oceans combined. While no sunlight actually penetrates the frozen exterior, the moon's subsurface sea could be warmed by hydrothermal vents, similar to those that support vibrant ecosystems in the depths of Earth's oceans. As we stand on the brink of a new era of space exploration, NASA's Europa Clipper spacecraft is poised to embark on a historic journey. The team at NASA's Jet Propulsion Laboratory is preparing to transport the spacecraft to Cape Canaveral in Florida, where it will be launched later this year. This mission is a significant milestone in our quest to understand our place in the universe. It promises to unveil new insights about Europa and potentially for life beyond our home planet. My colleague Merc Boyan, the Planetary Society's visual storyteller, gives us a peek into the clean room at NASA's Jet Propulsion Laboratory. There, the Europa Clipper spacecraft is undergoing its final tests before the next leg of its journey.
Merc Boyan here from the Planetary Society. I am in the clean room with the Europa Clipper spacecraft at JPL. Check it out. It's amazing to be in the room with a spacecraft that is going to make history. This is going to take pictures of things humans have never seen before, and it's going to learn things that humans have never known before. And it's right here. And it's way bigger than I thought it was going to be. I thought it was going to be a small car, but it's kind of like being next to an RV or a big van. And they say that when they put these solar arrays on, it actually fills out this whole room and goes way back. So it is the biggest spacecraft they've made at JPL. And it's beautiful. There's copper wiring, tubing going through all the instruments. What a work of art. Just an honor to get to be able to see this thing before it goes up in October. We're going to be wishing it the best of luck and waiting for all those pictures and the beautiful, beautiful data that we're going to get down from this amazing spacecraft.
I am Tracy Drain, and I'm currently the Launch to Mars mission manager for the Europa Clipper mission. I have worked on this mission for about 4 years, previously as a flight systems engineer, but I've been doing my current role for a few months now.
Okay, so have you been hands-on with this? Is this some of your handiwork we're looking at?
Oh, so that's the interesting thing about systems engineering. So we are the people who make sure that the hardware and the software are designed to work together to do a thing. But I very seldom, never get to actually touch the hardware. This is my first time in the clean room since the spacecraft has been in here, to be honest.
Oh, really?
Me too. Yeah.
Oh, wow. Okay. What kind of technological advancements have you seen in this mission compared to Juno?
So one of the things that's interesting about missions that are built by different entities, so JPL worked very closely with Lockheed Martin on Juno, and Juno was built on a lot of heritage from past Lockheed Martin missions. JPL partnered very closely with the Applied Physics Laboratory for Europa Clipper, including partnering with a lot of other companies who provided parts, and especially the instrument teams. So there are some similarities, but it isn't like there's like a direct line of ascendance from some of those things. One of the similarities I'll point out is something that you cannot see. Juno was solar powered. It has those 3 large wings on the spacecraft. This spacecraft also solar powered. They're not invisible. They're just not installed right now. They will get installed on the spacecraft in Florida. And because the spacecraft needs so much power, the solar arrays are huge. When the arrays are on and deployed, they will hang off the sides of an NBA basketball court. Junos are a little bit shorter than that.
Pretty much fill up this whole room? Is that
They're 30.5 meters end to end, so like about 100 feet. It's
okay.
big.
And those are already at Kennedy, right?
They are already at Kennedy, but they won't be installed until after this spacecraft is shipped to Kennedy, which is going to happen in late May for the ship.
So we have the satellite here currently undergoing some testing. We have it on our turnover fixture that allows us to rotate the vehicle in a horizontal configuration. Currently what you're seeing is the external portion of the spacecraft. The avionics module has now been closed for quite a while. And we have some of the science instruments here on what we call the nadir deck, which is this kind of a polygon shape down here. The tube that's sticking down is the NAC instrument, which was one of the cameras. Over here we have the my spectrometer. That's this red cover is the radiator of that part that's facing down. Over on the right hand side we also have the SUDA instrument. The one above that is the mass specs instrument, with a high gain antenna basically pointing up towards the sky right now.
And SUDA and mass spec are the ones that are going to kind of detect things in plumes?
Correct.
Okay. And you're saying it's doing a test right now?
We're currently undergoing testing. We're doing the GNC testing, which is guidance, navigation, and control. So they're right now, the way they explained it to us is the spacecraft thinks it's in space right now.
Okay.
So they have a number of cables hooked up that are putting signals into the spacecraft to make it think it's in a certain location, and seeing what the flight software is going to do and how it reacts to the commands.
Can you tell me about the camera? I mean, what kind of pictures are we expecting to see?
So actually, I recently learned this. So it's 1.5 feet per megapixel at a 16-mile distance from Europa itself. Mm-hmm.
Wow, so we'll actually see.
It's going to be pretty good.
Okay.
Yes.
Wow.
I'm Tim Larson, Deputy Project Manager for Europa Clipper. I started when we were in the just beginning the preliminary design phase on the project. Yeah, right after launch, we go through a very busy period for about 2 to 3 months where we're checking out the spacecraft, checking out the performance of the subsystems, tuning up all the controls on the spacecraft. Then we follow that with checkout and calibration of all the instruments. And so that all happens shortly after launch. We have a period after the Mars flyby where we have several calibrations planned with various instruments. And then we go through into cruise. We go in a relatively quiet period where we're just cruising on our way out, on the way out towards Jupiter. We do some periodic checkouts and maintenance on the spacecraft and on the instruments. And then late in cruise, as we get closer to Jupiter, we ramp back up our activities again, doing additional calibrations. There are calibrations that happen during the tour as well to track any drift in any of this instrument performance. The only quiet time will be about our mid-cruise period after we get past Mars and spend a couple years doing the Earth flyby and start heading out towards Jupiter.
I'm Preston Dykes, and I'm a public engagement specialist here at JPL. And I was inspired to my career by Carl Sagan and the golden record there. And so we didn't set out to create a successor to the golden record by any means, but we were sure as heck inspired by it. What we have here is the Europa Clipper vault plate. And what this is a very thin piece of the metal called tantalum. And it's an access panel that is part of the electronics vault. It's part of the spacecraft where we keep the most sensitive electronics and computers to help protect them from Jupiter's dangerous radiation. And some of the engineers who were developing that vault took a look at this blank piece of metal and got in touch with us in the communications office and said, can you guys do something with this? We think this is an opportunity to tell people about the mission and get them excited about it. We said, absolutely. That landed on my desk, and I've been happy for the last couple of years to help develop some designs with a team of people that you see now.
I am so glad that Merc had a wonderful adventure in the clean room. It looked like so much fun. I was going to be there, but unfortunately, I got sick hugging too many people during the recent total solar eclipse. It was absolutely worth it, though. No regrets. But in the name of planetary protection, I had to stay home. But a couple of weeks later, Dr. Bob Pappalardo, project scientist for Europa Clipper, came to the Planetary Society's headquarters in Pasadena, California. He showed us a replica of the Europa Clipper vault plate. Humanity has a long legacy of sending thoughtful messages and collections of names out into space. The Europa Clipper vault plate is a unique case, a symbolic message in a bottle that links our world with its vast oceans to Europa and the oceans hidden beneath its surface.
Thanks for joining me, Bob.
I am thrilled to be here, Sarah. This is wonderful.
It has been such a long road for Europa Clipper. You've been working on this for ages. There have been so many challenges along the way. So what has it felt like for you and the rest of the team now that you're this close to actually launching this thing?
It's amazing. It's surreal. It really is, to be able to go down to the high bay at JPL and see the essentially complete spacecraft with the ATLO engineers, assembly, tests, and launch operations crew working on the spacecraft. It's just unbelievable.
How far are we actually from launch?
Well, the launch period opens on October 10. So we hope to go as soon as we can during that launch period.
And then once it's actually out into space, how long do we have to wait for it actually to reach the Jovian system?
It'll be about 5.5 years from launch to Jupiter. So during that time, we make a gravity assist flyby of Mars, just 4.5 months after launch. And then we swing back around Earth for a gravity assist and then out to Jupiter. So all that takes about 5.5 years. Then it's another 11 months before we make our first Europa flyby.
And that's an interesting point because in this case, even though the spacecraft is on a journey to go visit Europa and study that moon specifically, it's not actually going into orbit around Europa. It's going into orbit around Jupiter, right? So I imagine it takes a little bit to finally get into that correct orbit.
That's right. And we orbit Jupiter instead of Europa because then the mission can last a lot longer and the spacecraft can be built out of more conventional parts that don't have to be as rad hard as you'd have to be if you're in orbit around Europa, right? Jupiter's acting like a giant particle accelerator, and Io's a litter bug, and the other satellites too, and those particles get ionized, and that means then they're rotating at the speed of Jupiter's magnetosphere, which is once around about every 10 hours. And that accelerates the particles to very high velocities and energies. So they're slamming into Europa, slamming into your spacecraft. We have flybys that bring us close to Europa, 25 to 100 kilometers off the deck, typically, and then out again where we transmit the data and get ready for another flyby.
So it's one of those Juno situations where it's in a really elliptical orbit that kind of takes it out of the danger zone, essentially.
Yeah, exactly. And Galileo had this approach as well.
That makes sense because the radiation environment around there, as you said, is completely insane. But during the time that it's actually in close by that moon, how is the spacecraft going to deal with that environment?
Oh, well, most of the sensitive electronics are in a vault. So there's aluminum shielding and tantalum that protects the most sensitive electronics in that vault. And Juno did take that approach. Of course, the detectors themselves need to be exposed, but those are radiation tested and a smaller fraction, if you like, of the spacecraft. So we're able to pay close attention to those parts that are exposed to the environment. So for each flyby, we rev up all the instruments a couple of days out and turn them on in sequence. And then, of course, it's a solar-powered spacecraft. So most of the time when we're far from Europa, those solar rays are tracking the sun. But then as we go in with all the instruments on, We go into a standard flyby configuration, which require the solar rays to be in a certain position to allow the radar antennas, which are attached to the solar rays, to be parallel to the surface of Europa. So we're on batteries when we're flying by Europa. And then only some time after the flyby do we then go back to put the solar rays charging from the sun.
How long is it actually going to be flying by Europa during these flybys? Because I imagine this thing is going to be clipping by.
We're going to be making observations of Europa from a couple of days out, but the heart of the flyby is kind of plus or minus 2 hours from Europa, when we're doing the gravity science and looking at it from afar with the cameras and the spectrometers. And then it's just the inner about half hour that we use the radar. So that's when all the excitement happens.
That's a lot to get done in a few hours. But thankfully, and we were speaking about this a little earlier in the office, this spacecraft actually is going to have enough power to be running all of the instruments at once. So we're not going to be having to make any hard decisions about which ones to turn on and off during these actual flybys.
That's right. This is a spacecraft designed for synergistic science, to allow all of the instruments to observe at the same time. And that means we're taking data simultaneously, so we can compare what we observe with, say, the plasma instrument compared to what we see with the ultraviolet instrument at the same time. And this also means that we're not wasting time in the radiation environment using just some instruments while others are potentially degrading from the radiation. And it also means we scientists can get along better because we don't have to discuss, debate, argue about which instruments to use for a given flyby. I was the project scientist for the first extended mission of Cassini, and we wanted to do a flyby of Enceladus to measure the gravity field, because that might be a way of confirming an ocean there. But to do so meant we couldn't use the other instruments. So, it was a negotiation and discussion, and the scientists said, it's worth it to do the gravity to help us better understand whether there can be an ocean there. We won't have to make that kind of very difficult trade for the Europa Clipper mission.
I imagine, too, that every time you pass by, if you didn't have all of your instruments turned on, you'd have to make some really quick, thoughtful decisions about what to turn on. Because this is one of those moons. We think there might be a subsurface ocean. And as we saw with Cassini, that moon is just spewing material into space. So any opportunity, if Europa actually has these jets, and we have some indication that it could, you wouldn't want to be having to make decisions on the fly about, now we got to turn on the spectrometer as we're flying through this jet. Now you can do it all at once and hopefully potentially capture some information about that.
Exactly. It makes the operation simpler. It makes the negotiations simpler. So the key things will be, okay, where do we want to point the camera? We'll have a plan for where we want to point it, but that might change as we approach a given flyby. Well, that's a relatively easy thing to change.
I'm really looking forward to these images. I remember hearing when Juno was in its beginning stages, ideation, that they didn't actually have an initial plan to put a camera on the outside. But the things that JunoCam has been showing us about the Jovian system, even just recently, those images of Loki Patera on Io with all that lava. Imagine what we wouldn't learn about that moon without the cameras. So what are you most excited about getting images close up of Europa?
Oh, so much. Europa is such a strange place that we only kind of partly understand. Like I love Ganymede, right? But we kind of get it. We kind of understand what makes Ganymede tick. Europa has these double ridges, for example, and the chaotic terrain, but we don't really know what they are. My training is in structural geology, faults and fractures as applied to icy moons. And Europa is just all that. So I'm going to be fascinated with, for example, these double ridges, which sometimes transition into wider bands. Well, how does that happen? Or these cycloidal ridges. There are these double ridges that make arcs across the surface. They're called cycloids, which is the absolute value of sine x. What's that doing on a planetary surface? So there's just so much. But we're going to be able to train all our instruments, not just the camera, of course. We'll be able to say, okay, and are there signs of organics there that we might see from the infrared spectrometer? we will have the gas and dust mass spectrometers on at the same time. And as we fly close, we can say, oh, look, there are signs of, say, organic particles or a specific type of salt that we're seeing as we fly over, and then we'll be able to tie those observations to the surface that we're flying over at that time.
That's going to be really useful to know because we're not exactly sure how many cracks there are on the surface, what kind of interaction there is between the outer surface of the ice and the inner ocean. And especially knowing the radiation environment around Jupiter, I'm sure there's some really interesting interactions on the surface that could potentially really enrich that subsurface ocean if that is happening.
Yes. So the radiation environment, while nasty for spacecraft or for organisms, and it can actually rip apart organic molecules if they're on the surface, so we'd have to look for fresh organic molecules if they're sitting there on the surface. That same radiation rips apart water molecules, H2O, to create H, to break it apart and allow the hydrogen to float away and the oxygen to sit there on the surface. And so it's those oxidants, which if they can get into the ocean, could potentially be a fuel for life. So we need to understand does and how does material get from the surface of Europa to its interior? And that's where the radar comes in, because the radar, it will be like taking a CAT scan of the interior of the ice shell to search for liquid water and other structures within the ice shell, and maybe will even penetrate all the way down to the ocean.
That's a really tricky thing, considering that we're not exactly sure how deep this ice shell goes. How are we going to be able to determine how thick it is and perhaps how deep that ocean is?
Well, believe it or not, the instrument that is most reliably going to give us the ice shell thickness is the magnetometer. Because, well, let me back up to the story of why we think there's an ocean at Europa. That comes from geological evidence. It comes from theoretical calculations of the amount of tidal heat related to the flexing of Europa as it orbits Jupiter. But the best evidence that there's an ocean there today comes from the Galileo spacecraft magnetometer. And that's because Europa seems to have an induced magnetic field, not really its own magnetic field generated within Europa, but an induced one because it's acting as a conductor as it moves through Jupiter's powerful magnetosphere. So this tells us that there's something conductive not too far down below the surface, and the most likely candidate is a salty ocean. So in doing that modeling, we're going to have so many flybys and such precise magnetometer data that we can estimate the thickness of the insulating layer that's on top of the conductor. What does that mean? That's the ice shell. So that's how we can best determine the thickness of the ice shell. And we're hopeful that the radar signal will be able to penetrate all the way through the ice shell to liquid water and bounce back to the spacecraft. But the requirement, the thing that we think we'll most reliably get is there water within the ice shell? Are there lakes within the ice shell? Are lakes related to chaos terrain? Is that how that chaos terrain is formed?
That's a fascinating idea. And I bet it is, but we won't know until we actually get there.
That's right. That's right. So stay tuned until the early 2030s. Right? It's going to exploration of the outer solar system is not for the faint of heart. We've been working on the Europa mission concept for a lot of years. Got the go-ahead Europa Clipper in 2015, and now here in 2024 we're going to launch, and we'll get to Jupiter in 2030.
That's actually not bad, considering I think the European Space Agency's Jupiter Icy Moons Explorer is reaching there in, 2031?
That sounds right.
So you'll be getting there just a little bit before them.
That's right. We launch later, but we have a more powerful rocket, the Falcon Heavy, and so we're going to pass our colleagues and their spacecraft. But we're working together with the JUICE team informally. We have conversations with them and say, we're going to have two spacecraft there at the same time. What kind of great science can we get from analysis of data from both spacecraft? Or are there any changes to the observation plan that we want to make that will help ensure we get great science by being there at the same time? One of the Europa flybys that we make, the JUICE spacecraft will be making a Europa flyby 4 hours different in time. I'm trying to remember which one encounters Europa first. But that will allow us to look for any short-term temporal changes in the magnetic environment and the plasma environment. So that's going to be really exciting.
That's really wonderful. I mean, I know JUICE is going to be looking at Europa, but it's also looking at Ganymede and Callisto, I believe, the two other larger moons. So that synergy could be really helpful. If only the Juno spacecraft would last that long.
Yes.
We can have three at once.
So JUICE makes 2 flybys of Europa and mostly concentrates on Ganymede with some Callisto. So Europa Clipper won't formally be doing science at Ganymede and Callisto, but we do have flybys. We're going to have a flyby of Ganymede very early before Europa to test out all of the instruments as sort of a trial run. We're going to do the observations in the same sequence that we would at Europa to make sure we've got this down. And that'll be exciting data to compare to what JUICE does.
Well, I'm sure that these moons in some way are all related to each other in the way that they developed and formed over time, because they're all, I mean, they're vastly different, but they're also very similar in a lot of respects. And I bet it's because of that radiation environment and the brightness of Jupiter as it formed and their distance across all of those.
Right, exactly how that works as to whether they started out somewhat similar and then Io and Europa lost a bunch of ice because Jupiter was warm, or what was the role of tidal heating, and you have more heating at Io and Europa, right? That's not completely certain, but there's certainly evidence of a temperature gradient among the moons, which makes it, analogous to a mini solar system. Just spectacular. I owe my interest in planetary science to the Voyager encounters of Jupiter back in '79 when I was in high school. I keep way too much, but I was recently going through some boxes and found my write-up about the Galilean satellites for some report in an English class. So I know even back then I was fascinated by them.
Just the other day, I was cleaning under my bed and I found one of my kids' books about the solar system. And it was those same images from the Voyager spacecraft that just lit my mind on fire.
Yeah,
but imagine
exactly.
Now we're going to get these up-close, amazing images of these moons. What we have so far is already just absolutely spectacular. But Europa is one of those worlds that just has absolutely captured the imagination of scientists and people in sci-fi for ages, right, since we knew it existed.
Well, and since we speculated there might be an ocean there, right? Because essentially everywhere on Earth that there's water, there's life. So could there be life at Europa? So Europa Clipper isn't specifically searching for life, but for the conditions of life, for habitability, the ingredients for life. So if you like, it's the first critical step toward a search for life there. If we find evidence for liquid water in the shallow subsurface and evidence for plumes or areas that are especially warm or have organics, then I think it will be compelling to do a follow-up mission with a lander that actually scoops up some of this dark reddish stuff and searches for signs of life there.
The problem with any of those ideas is that we need to worry about planetary protection in those cases. And as we saw with Cassini going around Saturn, just to make sure that places like Enceladus were safe, we ended up crashing Cassini straight into Saturn in order to burn it up. Are there similar concerns with this spacecraft? And what is the ultimate fate of Europa Clipper?
Yeah, Europa Clipper can't crash onto Europa because of planetary protection concerns. But the nominal plan is to crash onto Ganymede. And that one's okay, or Callisto, but Ganymede will get cooler science potentially because they may have oceans too, but below something like 100 kilometers of ice. And so it's very unlikely that material that crashes onto the surface of Ganymede could end up in the ocean. And that's the issue. We can't contaminate that ocean to keep it essentially pristine for future exploration.
I imagine that, it's going to take a while for this mission to get there, then for us to get all of the results. Maybe by the time we actually have a dedicated Europa lander mission, we'll have some better idea on how to sanitize the thing so completely that we won't have to worry about it. Because imagine if Europa is the first world that we find life on and we accidentally contaminate it. That would be horrifying.
Right, exactly. So there are planetary protection protocols and cleaning protocols for Europa Clipper to ensure that the chance of contaminating Europa's ocean is less than 10 to the minus 4. And so we've been able to demonstrate that to NASA and to the Planetary Protection Officer. Don't want to be arrested by the Planetary Protection Officer. But yes, it's more challenging if you know you need to put down your spacecraft onto the surface. Then you have to undergo more rigorous cleaning to ensure that 10 to the minus 4 parameter is still met.
We'll be right back with the rest of my interview with Bob Pappalardo after this short break.
Greetings, Bill Nye here, CEO of the Planetary Society. When you support the Planetary Society, you support space exploration. That means you are directly involved in making phenomenal moments in space exploration a reality. And that's why I'm seeking your participation in our Beyond the Horizon Every Member campaign. We're in the final phase of our 5-year plan, and we are more than 85% of the way to our goal of raising vital funds that will expand our core mission and strengthen the society. This campaign is critical to our future as the world's leading citizen space advocacy organization, and with your help, we are supporting new science and technology. You will grow the society to make our collective voice on behalf of space advocacy even stronger across the globe. And we are connecting more people of all ages with the passion, beauty, and joy of space exploration. Your gift of any amount today is an investment in the future and will help us usher in the next great era of space exploration. Let's go beyond the horizon. Let's make new discoveries. Let's keep going. Let's change the world.
How many passes are we actually going to get by Europa over the course of at least the main lifetime, the main mission of the spacecraft?
We get about 50 flybys during the mission, and that's enough to meet all of the, as they're called, level 1 science requirements that have been agreed with NASA. And if everything's going strong and the spacecraft is healthy and great science is happening as we expect, then there can be a discussion with NASA on potentially continuing the mission, having an extended mission with maybe a different focus based on what we learn.
Which is cool to know, because I thought that perhaps the Juno mission would be killed by the radiation at this point. And yet we are on to more and more of its extended mission, just getting cooler images of Io and other things as we go around, which bodes really well for the spacecraft, because that suggests that the radiation is not the thing that's going to be the end of the spacecraft.
Yeah, I was worried that it would be, or power, and they're related because radiation can limit the power generation of the solar rays. So when we consider the radiation environment and how much power we have, we always look at the worst case at the end of the mission. So more likely, I suspect it'll be propellant, that we might ultimately run out of propellant and have to plan an extended mission that uses up almost all the propellant, almost all because you need to know that you can then execute the final part of the trajectory, which would crash the spacecraft into most likely Ganymede, but potentially Jupiter or Callisto. Oh, and I referenced that there could be cool science that way. You could imagine an end of mission scenario where the JUICE mission is still there at Ganymede, and then along comes Clipper crashing into Europa and generating a new little crater, and maybe that could be observed by the JUICE spacecraft. Or if the Europa Clipper spacecraft lasts longer, maybe we can go into an area that's been characterized and shown to be interesting by JUICE that maybe some future spacecraft will come observe where we went in.
Those images of the crash site would be absolutely bonkers. And I imagine maybe 300, 400 years from now, humans could go over to Ganymede and actually see that crash site. I would go on that vacation. That's amazing to think. So we have at least 50 flybys, and potentially more, depending. What are some of the things that you personally are most interested to learn about Europa as we're going through this mission?
I want to know, how thick is that ice shell? I want to know if that ice shell is convecting. So the mantle of the Earth is convecting, meaning warm rock rises up and cold rock sinks, and this drives the plate tectonics of our planet. At Europa, the ice shell may be thick enough that the warm ice at the base of the ice shell, where it's contacting the ocean, wants to rise up toward the surface, and colder ice near the surface sinks down. So the ice shell itself may be convecting. There's no place on Earth where an ice sheet is thick enough to convect. But at Europa, depending on the exact properties of ice and grain size and tidal squeezing, something like 20 to 30 kilometers thick, it should be convecting. So there might be parts of the ice shell, or maybe the whole ice shell, that is convecting like this, kind of like wax in a lava lamp or miso soup.
I mean, maybe that would explain the weird terrain on that moon. We've seen a lot of moons out there with icy shells, but there's just something really wacky about Europa. That would explain a lot of things for me.
It could, right? The convection could make these pits and spots and domes that we see. Maybe big blobs could create the chaotic terrain. That's kind of the mental picture I have of Europa, but it could be all wrong, right? We need to test hypotheses, and that's why we're going there.
I'm sure we'll be wrong about something. I mean, as is tradition, anytime we get close enough to a planetary body that we haven't been to before or haven't gotten a close enough look, it always throws us for a loop. So I'm expecting to be completely surprised.
Yeah, if we're not wrong about stuff, we're not learning, right? We're not asking deep enough questions.
You mentioned earlier that a lot of these different instruments are held inside of a vault. Something that I think is very meaningful about this mission is that it's another one of those that's carrying human messages with us out into space. And in this case, you're doing it with a vault plate. Is the vault plate named that because it's actually sealing the vault?
Yes, exactly. There are several areas of the vault where the last thing to go on will be these triangular plates to cover up areas where there have been some cables that pass through. And so when we were inquiring along with our communications team, might we be able to have a message on our spacecraft? The spacecraft team came back and said, yeah, one of these vault plates, you can have both sides. And it's about like an 8.5 by 11 piece of paper cut diagonally with kind of rounded corners. So that's pretty much the area we had to work with. And we worked with our communications team to throw out ideas for what kind of messages we might want to include there.
In a lot of other cases, we've sent these messages out into space. Voyager is a great example. This vault plate is being compared to the golden record that we sent out into interstellar space at this point on the Voyager spacecrafts. You know, I imagine that this is more of it's kind of a message for us more than it is a message to the Europans or whatever extraterrestrials might find it, which kind of gives you a little more freedom to add whatever you want to it without having to consider how would an alien interpret this.
That's right. Our goal is not to talk to the Europans. It is to talk with ourselves. And of course, the same could be argued for Pioneer or Voyager, but yes, there's a chance that it could be found someday. But really, those two are much more to educate ourselves. So, okay, so here we'll go with that and say, what do we want to communicate? What do we want to talk with the public, talk with our inhabitants of our planet about in thinking about space exploration? So we knew past spacecraft have collected signatures and said, send your name to space. And we thought, well, we're not any mission. We want to do something a little more special. Instead of just sending your name, what if people are co-signing a message? They're essentially acknowledging this message that's going out to Europa and being part of that. So then, of course, the question is, what message? Who writes it? And for, I don't know, weeks to months, we were tossing out names and thinking about who might be the right person to write such a message. And then we all converged on the poet laureate of the United States. Let's see if she would agree to do it. And our comms team reached out and gave a presentation, and I've heard interviews with Ada Lovone, who said, well, why are they telling me all this? And then the ask came, would you write a poem for the spacecraft that's going to Europa? And thank goodness, fortunately, she said yes. And then she's explained that, she said yes. Now what? How to write that message.
No pressure.
No pressure. I wouldn't want to have to do that. It means a lot to me personally that we had the poet laureate write this beautiful poem for Europa. My mom was first a proofreader and then a special education teacher, and through her whole life wrote poetry. So it's extra special to me that we have a poem going to Europa. And poetry can convey big ideas in a small space.
I now work in science communication, but the first ways that I learned how to communicate was through my high school's creative writing club. And we would share our poetry all the time. And I'm sure someone from high school remembers my weird poetry about planets. But I remember being very moved when I heard Ada Lovone's poem for the first time. And some of my colleagues were actually at the unveiling where she got to read that poem aloud. Were you there as well?
Yes, in Washington, D.C. It was quite a moment. We had a preview of the poem beforehand, but it just brings tears to my eyes when I hear it. And it makes that connection between us on Earth, one water world, to another Europa.
That's what's so fascinating about it. As different as our worlds are, I mean, the necessary materials for life seemingly are all there. And it's easy for us to find water worlds in our own solar system. It's going to be far harder to find them out there among the stars. So beginning to make these connections between our worlds could be the foundation of whole new branches of science and our understanding of life in the universe.
Exactly. That's why Europa exploration is so important, to understand if we have the ingredients for life, as we suspect, but Europa Clipper, we need to test these ideas. Then did life actually get going? And if so, life at Europa would almost certainly be independent of life on Earth. So early in solar system history, if life got going on Mars, it would get tossed back and forth between Earth and Mars by big impacts. That is very difficult to happen between Europa and Earth. So there wouldn't be exchange of spit in the early solar system like there is or was between Earth and Mars. So life at Europa would almost certainly have an independent origin. So imagine if there is life there, what it would mean for the science of biology. Does it use DNA? Does it use ATP? Does it use the same 20 amino acids? Probably not. What would it be like? And that could revolutionize our understanding of biology, of life.
Any small indication that there could be life elsewhere, anywhere in the universe would be huge. But being able to find it in our own solar system, that would be so magical, because it would unlock that potential to really allow us to see what life truly is outside of our human Earth-centric perspective.
Right. And yes, and if there were life in two worlds in one solar system, that would be huge. Also on our vault plate is the Drake equation in Frank Drake's handwriting. And of course, one of those factors is what fraction of planets within a habitable zone does life actually come to be, right? So we are going after one of those parameters of the Drake equation with the Europa Clipper mission.
Would you mind pulling out the vault plate so we can look at the other details?
I'd love to. I just happen to have a vault plate here.
And to be clear, this isn't the vault plate that's going to be on the spacecraft. This is a replica of the vault plate.
This is the vault plate that was revealed at South by Southwest just a couple of months ago. Ada Lovone and Lori Glaze, the director of the Planetary Science Division of NASA, unveiled the plate and its message. This was the test plate to test out the engraving onto tantalum and to make sure the process was working. And I understand that the one that goes on the spacecraft was just finished, and is next going to have the chip with the over 2.6 million signatures engraved onto it. Keep in mind, those aren't encoded in it. They're engraved onto it. They're actually micro-engraved onto that chip.
That's a lot of effort considering that we don't think anyone's going to find it. But at the same time, does that mean that you just need like a really fine microscope in order to see the names on there?
Yes, you need a powerful microscope.
Because my name's on there. That'd be really exciting.
So here it is. This is the test model, if you like, of the vault plate. We also had the chance to bring it to our Europa Clipper science team meeting. I'm wearing gloves to not damage it because we don't want fingerprints and Mars on it. So on one side is the poem for Europa by Ada Limon, written in her own handwriting and signed. There is also a hand-drawn sketch of Ron Greeley. Ron Greeley led a couple of the science definition teams that helped shape the science that we're going to do with the Europa Clipper mission. He passed away several years ago. He was a mentor to many of us and was my thesis advisor back at Arizona State University.
That's so special.
We have the Drake equation up here on the top in Frank Drake's handwriting.
How did you get it in his actual handwriting?
SETI had a couple of versions that he had written out. You can see a pretty well-known picture online of Frank Drake drawing out the equation on a board. Mm-hmm. And, of course, he passed away as we were coming up with this concept and thought it a fitting tribute. We also have representations of radiation emitted by hydrogen and hydroxyl, OH. And this is the area that's sometimes called the water hole, where SETI commonly searches for radio signals because it's a relatively quiet area of the radio spectrum, and thought if there are civilizations transmitting, it might be near those wavelengths. And then we have a representation of the Galilean satellite system, very schematic, of the 4 Galilean satellites. And in the center of it there is our bottle, because we see this as a message in a bottle tossed out into space. And when you do that, it's for someone else to find, right? It's for someone else in some other day to look at the message and interpret it and wonder what might have inspired it and who put it together.
I don't know enough about tantalum to know its like tensile strength, but we don't imagine this plate will survive impact on Ganymede, will it?
Unlikely, but I don't think we've done that math. That would be worth finding out.
That'd be really cool.
On the other side of the plate is an amazing design that represents the waveforms of the spoken words for water in 103 different languages. So we had linguists come up with a list of languages that represent all of the world's languages. And for those 103 languages, we had native speakers speak the word for water, recorded it, transformed those into the waveforms that are here, and put it together in an artistic design by a professional designer. And in the center is a representation of the American Sign Language word for water. So that's there as our 104th language.
That's so beautiful. Is there anywhere online that people can actually listen to these recordings?
Yes. If you go to the Europa Clipper website, you can follow the links there and you can listen. You can pick a language and listen to the word water spoken in that language.
I'll make sure I find the website for that and add it to the page for this episode of Planetary Radio. So anyone who's listening can go back and actually listen through these, because this is such a beautiful representation, not just of our connection to water worlds, but of humanity at large and all of the various ways that we think about this thing that is so important to not just us, but probably life in the universe. How many years have you been working toward this mission?
I joined my first science definition team that was put together by NASA in 1998. So I think that's 26 years. It's been a long journey.
And then you and the team are going to have to wait around for a few years while it makes its way out there. What are you and the team going to be doing during that interim as you're waiting?
Yeah, it's going to be challenging to help keep everyone together, right? As project scientists, sure, I help oversee the science. I'm the go-between between the science team and the engineering team. But also my job is to make sure the science team feels and is unified and motivated. And we'll have 5.5 years there where we need to stay connected. So we will meet about once a year to get up to date on happenings, on calibration as we're headed out toward Jupiter. We will have studies going on by some co-investigators on how our instruments can best work together to solve scientific problems. So we'll get updates on those. We're currently putting together essentially a planning guide for how to do the science at Europa. With every flyby, we're going to go through the same sequence of events, but we'll see different sides of Europa. We'll fly by different latitudes and longitudes. And so we're putting together this planning guide of what we can best do on every flyby to put together that holistic picture of Europa. So that'll be another effort to help unify the team and keep people forward-looking.
And then begins the decades of coming through the research afterwards.
Yes.
As we're seeing with even the Galileo spacecraft at this point, that old data is still gleaning amazing results. I imagine the stuff out of Europa Clipper is going to be illuminating things for us for decades, maybe even a century or more.
Yes, terabytes of data coming out of Europa Clipper.
And so begins a whole new branch of science as we analyze the water worlds of our solar system. This is a huge turning point for us, and I'm so moved to actually be able to see this vault plate up close and know that my name, along with so many millions of people's names, are going to be going along with the spacecraft and all of our dreams and all of our longing to know whether or not we're alone in the universe. This is beautiful. Thank you for sharing this with us.
Thank you for summarizing it so well and for having me here. And it's just a wonderful opportunity to be able to talk this through.
This is the beginning of something so beautiful and might help us answer some really deep fundamental questions about ourselves and the universe. And I know I'm speaking for most of the people listening. We are so grateful for everything that you and the team have done.
Well, thank you. We do it for the public, right? I mean, we do this because it's in our hearts, but we're doing it for others because the demand is there. The desire is there to understand what's out there. What is Europa like? Could there be life there?
Thanks so much, Bob.
Thank you.
Now we go to Bruce Betts, the chief scientist of the Planetary Society, for What's Up.
Hey, Bruce.
Hey, Sarah.
Coming to you from Washington, D.C., yeah.
Ooh, how official.
We're about to have some interesting times advocating for space in Congress. But in the meantime, last week I got to talk to Bob Pappalardo about the Europa Clipper vault plate and actually see it in our office, at least a replica of it. It was really cool in person getting to see one of these messages that we're going to be sending out into space. And I know the Planetary Society has been sending messages out into space for an age. And, you know, it's part of the spirit of Carl Sagan and that golden record on Voyager that got sent out there. What are some of the coolest things that you think that humans have sent on these messages to space?
Oh, I mean, I'm, of course, partial to the things that we've done over the last few decades. So the Mars exploration rovers, the landers that they drove away from, have silicon glass mini DVDs, have 4 million names of people who wanted to send their names to Mars. We actually started it on the ground floor of sending names back with Cassini. Before I was officially involved with Planetary Society, it was back in the days of signatures and scanning them. Our volunteers scanned them, and they were sent on Cassini off. They're now part of Saturn. And we had a whole huge program we talked about a few weeks ago, Red Rover Goes to Mars, with the Mars exploration rovers, but also on Phoenix, we sent a library. So there's a Mars library on a mini DVD that is called Visions of Mars. It was originally created most of it for the failed Mars 96 mission, but then we updated it and put it together and negotiated with the project and got Peter Smith on board, who led the project. And so on Mars, you've got all sorts of Mars-related science fiction, science fact, and greetings from people. And so that's pretty nifty. We've got Arthur C. Clarke and Carl Sagan himself, because he recorded it for the original.
Oh, that message to Mars. I think one of the coolest things that I personally was very moved by, I mean, there's a lot of things that we sent off on the Voyager Golden Disc that I thought were really beautiful, but maybe about half a year ago, Matt Kaplan and I and our other colleague, Amber Trujillo, went to go see Anne Druyan, who was Carl Sagan's life partner. She was at an event at Caltech, and she was speaking about the experience of having her brain waves recorded so they could put that onto the Voyager Golden record, and all the things that were going through her mind, just like thinking about love and life in the universe and all these interesting things. And that's a really unique thing that we sent to space. But more funny, I think personally, and awesome, is that the Japanese on their Akatsuki mission sent some of Hatsune Miku's music, who's like a really popular Vocaloid pop artist in Japan. And that just cracked me up when I learned it. So those are my two.
No, that's good. I mean, I think there's a great, profound nature to even just sending names. So we've championed that. NASA's taken up that mantle, and they collect names for all their missions. And, on the one hand, it's silly, but on the other hand, it's not, because you're getting involved with the mission in a real way, a small but real way, and sending humanity out into the universe. And we've been involved with sending our memberships names all over the place. We've taken messages of various kinds, including for some of the Japanese missions that we've collaborated with, and for LightSail too. And so our members, as well as those many millions who've signed up, have gone out there and explored in a way that most of us do in a physical way. So I find that mildly profound just in and of itself.
I wonder how many places in space your name is, Bruce.
Yeah, blacklists.
I know my name is on a bunch of spacecraft, but I've never kept a record of everyone I signed up for. So maybe I'll go back to those websites. I know there's usually a website where you can look up whether or not your name is on that spacecraft. I should probably look that up and make myself a little record so I can remember that someday.
Yeah, if you got started with any of ours, it's on Messages from Earth if you search that in the Planetary Society. And some of them you can get still print certificates, and some of them never had them, and some of them go too far back, but it'll at least tell you the ones we've been involved with. And as I say, NASA particularly, is we did that with them in collaboration with them and LEGO and with MER, but then since then they've developed quite the pattern of doing this. And it's neat. You want to hear something neat?
Yes.
We move on to
Random Space Facts.
On the Phoenix Visions of Mars. I just think it's kind of profound. If you're familiar with H.G. Wells and then Orson Welles, different spelling, characterization of the War of the Worlds involving invaders from Mars. Both the original radio episode that freaked out people who thought it was real, and the text of the book are included in Visions of Mars. So I think we one-upped them and got to Mars before they got to Earth.
That is a fun random space fact. It still tickles me that people thought that was real. That's so great.
I mean, I totally did.
Did you really?
Wow. How old do you think I am? Okay, never mind. Don't answer that question.
It's all relative. It's all relative.
All right. We done?
I think so.
All right, everybody, go out there, look up the night sky, and think about dogs in space. Thank you, and good night.
We've reached the end of this week's episode of Planetary Radio, but we'll be back next week with an interview that I cannot wait to share. I'll have to leave it a surprise for now, but fans of science fiction are going to enjoy this one. If you love the show, you can get Planetary Radio t-shirts at planetary.org/shop, along with all other sorts of cool spacey merchandise. Help others discover the passion, beauty, and joy of space science and exploration by leaving a review and a rating on platforms like Apple Podcasts and Spotify. And remember, we're now on YouTube and YouTube Music's podcast section. Your feedback not only brightens our day, but helps other curious minds find their place in space through Planetary Radio. You can also send us your space thoughts, questions, and poetry at our email at planetaryradio@planetary.org. Or if you're a Planetary Society member, leave a comment in the Planetary Radio space in our member community app. Planetary Radio is produced by the Planetary Society in Pasadena, California, and is made possible by our dedicated members whose names are etched into spacecraft from Earth all the way out into the interstellar void. You can join us and help us explore worlds, find life, and defend Earth at planetary.org/join. Mark Hilverda and Ray Paoletta are our associate producers. Andrew Lucas is our audio editor. Josh Doyle composed our theme, which is arranged and performed by Peter Schlosser. And until next week, Ad Astra.